is that we can use objects like, this is a black hole. It's not a real picture, but it's a lovely computer simulation of a black hole. We can use space-time on the largest scales like black holes to understand string theory, and to use string theory to understand black holes. Would you be willing to reflect on that for a minute?
Yeah, and there are many reasons why that's an interesting place to do that. One is that it turns out, although you hear things about black holes and they sound very exotic and what have you, it turns out black holes are, I think by almost any definition, the simplest objects in the universe, either in the theoretical universe on the page, or even the kinds of black holes that you're hearing about being discovered now explicitly because they collide and coalesce and send off gravitational waves.
Ray Weiss was here last month.
Oh,
we talked about
so you're all experts. Great. So it turns out black holes are incredibly simple. And what theorists love are simple laboratories for ideas. And so it turns out that a black hole is very simple, but it also ends up being at that sort of just on the edge of our best understanding of gravity from the side of Einstein's equations in 1915, etc. They're the simplest, some of the simplest solutions you can write down of those equations. But then also just the fact that they have this thing called the horizon, this apparent place of no return. Quantum mechanics doesn't play nicely with such one-way barriers. And so it tells you that there's an interesting opportunity to understand black holes, and hence an interesting non-trivial solution for space-time in the presence of quantum mechanics. And so going back, for example, you know, the reason why Stephen Hawking, one of the main reasons he's famous is because his discovery that that's a place where you can actually learn things without even understanding a full quantum theory of gravity. You can get a profound statement about aspects of a quantum theory of gravity by looking at black holes. So coming to string theory now, even though we're still flailing around to try and understand how best to find ways of describing all of the kinds of particles we've seen and what have you, the good thing is that there's one space-time, as it were, there's gravity, and then you can ask, in the context of string theory, what it thinks of black holes and quantum mechanics. And it turns out to be a relatively simple question that you either get right or you get it really wrong. And so it became an incredible test for string theory.
So you were referring to the fact that Hawking asserted, by looking at quantum mechanics around a black hole, that the black hole could steal some quantum particles from empty space, leaving others free to radiate.
So yeah, he essentially he discovered that black holes actually aren't black. So right. String theory, you know, string theory isn't the theory of strings. Black holes aren't black. Yeah.
I hope it's all clear now.
Right.
No, but what Hawking did.
Okay. Oh yeah. So, and I'm sure you'll take this in an interesting direction, but let me finish the point. Here, this opportunity to put together, if you like, a little bit of our understanding of quantum physics in the 70s and a little bit of our understanding of how that would work quantum mechanically, told you a very robust result about not just that black holes are black, but they're black in a very specific way. They radiate in a particular way, and they have a certain property that you should, in a full theory of quantum gravity, if you ever had one, be able to calculate. And you'd either get that right or wrong.
Right, so basically they're hot. We know how hot they should be. They should be radiating, emitting, and they're actually quite cold, basically. Most astrophysical black holes are quite cold. The bigger the black hole, the colder.
But there's a temperature you can compute.
But there's a temperature you can compute, and you're saying in string theory, your task is go compute that temperature if you assume that string theory is correct, and do you get it right?
So it's
not the temperature, the entropy.
Yeah. So it turns out that it isn't quite the temperature, but it's a related thermodynamic property called the entropy. And I'm sure you knew that, but temperature is more accessible. Yeah.
Exactly.
So there's a thermodynamic property. There's a relationship. Okay. So there's an entropy. It's a thermodynamic property which all ordinary substances you can associate with it. It turns out magically, it seems, for a black hole, there's a geometric property which is essentially the area. If you think of the black hole as a ball, that's like there's an area you can compute of that ball. And you divide that area by 4, and in the right units, that's the entropy. And it seems like a magical result. It's very robust. And then the challenge is, if anyone writes down a quantum theory of gravity, the test of that quantum theory of gravity being on the right track is that they get that right. And so string theory could have failed at that point. And it took a long time to find the right way of doing that computation honestly. And finally, in 1995, Strominger and Vafa actually did that, and they got the number on the nose, and that was sort of amazing.
For one special. Yeah.